Hi, so today I'm going to show you how you can get two microcontrollers to talk to each other via serial. This is quite helpful when you want to separate the two devices. For example, if you have one microcontroller really busy doing something very time critical and you don't want it to be bogged down by anything to do with display or data output, you can get a second device to actually display that data, to do data sort of analysis on it or data logging. So this is what I'm going to show you today. So this is the topology of this demo. I'm using two microcontrollers. They are STM32 series with the I'm using them with the Arduino IDE. Some of you might know about STM32 Arduino. It's a project which opens up the Arduino IDE to work with the STM chips. The principles are the same if you have Arduinos or anything else. On the left here we have the device which has the data, and on the right here we have the device which is displaying the data. So the way this partnership works is that the right hand device sends a byte over serial, and this device is monitoring the serial port for that character. If it recognizes that character, it puts together a data packet which consists of data that's come from this potentiometer, and it sends it across. And then this guy displays it on the OLED. Simples. And this is the actual project here. So we have the left-hand device here, which is the ECM, is what I'm calling it. It has the data from this pot here. Then it sends, well, the serial line is connected to this device, which is the display. So this device requests data from this guy. This guy then sends the data. It's received over here and it's displayed on the screen. If I position the camera so you can see both, if I turn this pot here, you can see that data change. So it's very fast, very snappy, very minimal lag. It's a very robust way of exchanging data. It's much more foolproof than an I2C connection or anything else. Right here in the middle we have the serial line going into the breadboard here, and we are tapping off into this cheap little logic analyzer. These are great tools to actually try and figure out what's going on the bus. When you're communicating data, it's absolutely invaluable. So let me set this up quickly and I'll show you what the data is that we're working with. So this is Pulse View, which is a free bit of software which interfaces with the logic analyzer. So we just need to set up the correct data types. So we have UART data, receive line is channel 0, transmit channel 1. May not work this way around, but we'll flip it if it doesn't. Decimal data, why not? We need a faster capture rate and we need more samples. If I run this capture, here we go. So what we are seeing here is the data packet coming from this guy requesting an update. If I change this to ASCII, this is an R, exactly like it is in the code. So the R is then received by the ECM, and the ECM returns a bunch of data. We've got the opening bracket to show the beginning of the data, and then we have 3 bytes, and then we have a closing character here which closes the data packet. So if I change this to decimal, we can see 97, 48 and 24. 97 is the actual read, the analog read from the pot here, and these 2 bits of data are, this is half 97 and this is a quarter of 97. just dividing the original value, just trying to make things more interesting by having 3 instead of 1. And what is quite interesting is the delay here between the data, the request being sent out, and it being returned. So you can see it's about 6 milliseconds, which isn't too shabby, but as you can see, it does vary ever so slightly. Actually, I think what is happening here is this packet is the answer to this request here. So actually, it's a longer delay. Anyway, even if you crank up the speed, and so even if you crank up the bus speed and the request rate, this system is robust enough that essentially what you'll be receiving is just a slightly older packet. The data won't be wrong, it will just be delayed slightly. And this delay is very manageable for me. You can also see some interesting patterns here where there's a longer delay here than the others. And this is probably to do with the wire library and the I2C communications with these little OLEDs, because the I2C protocol is actually quite heavy, I2C. So that's where the delay is coming from there, you can see. So yeah, interesting stuff. Okay, so now you've seen the devices working, let's go through the code. So this is the left hand side device. This is the ECU with the data. It's the slave in that configuration. So it's receiving the request and sending out the data. So we start off with the usual stuff. Wire is the I2C library, the Adafruit graphics library, and then the subset of that library, the SSD1306 STM32 version, for allowing us to run that little OLED display. Then we have timer object, which is a great library simplifying the timers in Arduino IDE. Usually you have to do non-blocking timers, you have to count millis and then compare. Usually you have to deal with counting millis and subtracting the previous millis from the current millis to work out the time elapsed, and then if that time is more than the interval, blah blah blah. It's really confusing, not human readable very easily. This library just wraps it all into like a very simple object oriented system. So we'll go through it when we get down to that part. So carrying on, OLED address, I2C address, which could be different with your display. Then we have the pin definition for the pot pin variables, so PB1 in this case. So STM32 ports always start with a P, and then so it's like port B and then pin 1 of port B. So there's loads of pins on port A, loads of pins on port B, loads of pins on port C. This is the system you use with the STM32 Arduino core. And then we have the instance of the Adafruit I2C display. Pin out, pin connections for the VET6 board. Same actually, I think, for the Blue Pill as well. And then we have a new object of timer object called simulated engine params. So every 100 milliseconds, this is the interval for this timer. And then we have a couple of variables. We have a array which holds the temporary data until we actually fill it with real values. The less than, data 1, data 2, data 3, and then more than, which closes the data packet. Then we have a bunch of bools and bytes for the actual serial data transmission stuff. Carrying on, we have the setup. So in here we're setting the I2C bus speed to 400 kilohertz, which actually hugely helped in my situation because the default speed is 100 kilohertz. It's fine, but the I2C library is really heavy. Well, it's not the library, it's the protocol. It's really heavy for these microcontrollers, and they don't deal with it very well. If you have it running constantly, it really slows down the microcontroller. And actually I found that at the clock speed of 100 kilohertz, the response time between the ECM receiving the request and sending it out, the response time actually halved when I went from 100 kilohertz to 400 kilohertz. So that actually shows that you should set it to 400 if your devices can support it, because it speeds up the rest of the MCU. I'm not sure what it's like with Arduino. I think it usually works okay, but people usually don't notice the speed difference unless you've got some timing critical stuff. So then we have, we begin the display, we clear the display. Here we're saying when that timer has elapsed, so when the interval has passed, do this function, and this function engine params update is down here. All it does is basically creates the data packet for us, and then here we start the timer, initialize the serial 2 port at the baud rate of 115200. It actually works at 9600, and I also tried it with a 250,000 baud as well, and it was okay, but I chose to just settle down with 115200 just because it's kind of a happy medium. So carrying on into the main loop of the program, we've got this function here, receive bytes with start end markers. This is the kind of the serial data, the serial comms loop here. So when we actually go into it, it's only executed if there's something available on serial 2 and the serial 2 buffer. If there's nothing, we just carry on. So carrying on, we read the pot value. That variable holds the value. We divide it by 16 because in the STM32 world, the ADC is can't remember how many bits. I think maybe 12 bits. So the highest value is like 4000 something, and in the Arduino world it's 255. So we divide it by 16 to bring the value back down to 255, just because that's the highest value that you can hold in a byte of data. So yeah, we scale it down just with a simple division. Then there's a bunch of OLED stuff, so we just draw some pixels, clear the screen, construct the actual text, and then we need to update the timer. So the way the timer object library works is that we need to run this in every loop. That just keeps calculates the time that's gone by, keeps track of time basically. So let's just say we have data in the serial buffer and we branch off into this function here. Not branch off, we shoot off into this function here. We read the serial into RB, and then we check if RB is the stats update request, which happens to be letter R. So it's hex 052, hex 52 value. So if we receive that value, we do engine params update just to refresh the data array with the latest values from the pot, and then we send out that data. Done. That's all it is in this part. And then moving on to the display. This is the display code. This is the right hand device. So there's a bit more code here, but let's go through it. Same stuff as before. However, we're using a slightly different controller for the 1.3 inch OLED. This is the SH1106. The STM32 version of this library was broken because of an update that the STM32 guys did. So they used to have two different wire libraries, hardware wire and software wire. This library was originally written to work with the hardwire ITC library. I had to update this to work with the updated wire library because hardwire is now just wire. Anyway, you find this on my GitHub. I will put a link in the description so you can get this working yourself if you like. And the rest is the same here, so even the same pins for UART2 and for the I2C clock and data lines. We instantiate the display again. -1 is the reset pin. We don't need to use a reset pin, so this is just -1. Usually it's a pin port number. I've defined an internal LED here, basically just to provide a visual feedback of serial action, and then I have a boolean for the LED state to allow it to blink. So again, same as before, we have a timer object. This is set to 50 milliseconds. So every 50 milliseconds we're going to send the request. So this is the name of the timer and this is the interval. Couple of variables. This is all stuff related to the serial comms. Same setup as before. We set the wire clock speed, the I2C bus clock speed to 400 kilohertz. Clear the display. We define what function we execute when the timer's up, which is request update data. And then we start that timer. We initialize the baud rate for serial 2 OLED stuff. Then we go into the serial function here. So this serial function has code both for receiving and sending data, whereas the other one just had code for receiving data. When there is data in the serial 2 buffer and we're not currently reading data, it's red. The LED state is toggled digital right, so that toggles the LED from on to off. And then we check for the start marker and then the end marker. We construct the data array with the bytes of data, and then we set the new data flag to false again. So we've just constructed the data packet and we're ready to receive the data again. And that's all it is. So when this data is constructed, it goes into received bytes. It cycles through however many bytes of data you have in the array, and it builds the array for us. So array value 0 becomes the first piece of data, array value 1 so it's the second piece of data, and 2 is the third piece of data. And because the original data originates from a potentiometer, and I forgot to mention actually before that in the left-hand devices code we actually scale the data down. At this point it's just arbitrary data, and the original ECU pop-in value is from 0 to 255. For the second byte of our data array, we just divide it in half and then divide it in half again, so 4 times a quarter, just to make the bits of data, I don't mean bits, just to make the bytes of data slightly different from each other. Yeah, so when we receive this data at the display end on the right hand side, we scale it back up to something that makes a bit of sense. So our first bit of data was, let's say, RPM multiplied by 10, just because the data that we can represent is between 0 and 255. That doesn't actually represent any usable RPM, so we scale it by 10. So 100 becomes 1000, a bit more usable data. We'll still top out at 2550 RPM, so it wouldn't really be usable in the real life engine scenario. You'd have to use 2 bytes to represent that value, which will give you up to 16,000. So you'd have to do a bitwise calculation to add the two array values together and represent that data more accurately. The second piece of data is temperature is just a straight byte as we receive it. We convert it to string and display it. And then the third piece of data, we can't send a float, so we convert it into a byte, and then we essentially unconvert it down. So the voltage was let's say 11.96 at the measuring end. So we times it by 0.1 to turn it into 100 and what did I say? 119 it would be, so 119. And then at the receiving end, we would divide it again by 10 to get 11.9. So we'd lose that last decimal point, but it would still be good enough for most purposes. So that's what we're doing here. And yeah, that's pretty much it. My demonstration is kind of a master and a slave, but you can actually merge the two pieces of code together. So each device can send a request to the other device and the other device. So each device can actually communicate data to one another. So you just have to replicate this serial code into the other device. So I hope that's been helpful for you. If you have any questions, stick it in the comments below, and thanks for watching.